Good morning, folks. This is Todd Coburn of Cal Poly Pomona with Lecture 4 of Aero 4080. Today we're going to be taking what we learned about truss elements and extending that to look further at how we would deal with two-dimensional trusses with multiple elements. So before we get started, let's quickly look over what we've learned to date, because this information is going to be critical to being able to build on this foundation. First, to summarize our elements, we have one-dimensional truss and spring elements. This is the nomenclature for each of these elements. It's important that we understand this. In both of these cases, we have two nodes. We have x, positive x, which is defined from node 1 to node 2 of that element. And for the springs, we have a spring constant of K. For the trusses, we have a spring constant of AE over L. That's our stiffness matrix for the truss and our stiffness matrix for the spring. With that said, we have our local coordinate relations relating our forces to our displacements through the local stiffness matrix. And this is the detailed nomenclature of our truss elements. We have a force that's only oriented axially along the element at node 1 and node 2, and displacements that are also axial along the element. Okay, we could have called these, the book calls them K prime, F prime, and D prime. We can call them K local E for element, force local element, and displacement local element. Okay, that will more precisely denote what they do. We saw transformations where we learned to transform these one-dimensional elements. We looked at this for trusses, but the exact same approach is used to transform our one-dimensional spring elements. This is how we transform local coordinates and global coordinates. Okay, where we defined our T-star matrix relating our local to our global coordinates. All right, when we have a 1D element in 2D space, we saw we needed to do that transformation. This is our relation for relating our forces, our local forces to our local displacements. Our local stiffness matrix we can define this way. For a two-dimensional system, we're going to generally need to turn that into a 4x4 matrix, which translates our little 2x2 matrix into this 4x4. And we can relate our forces to our displacements now in 2 dimensions, where before this one-dimensional element only had a displacement and a force along its length in one direction. Now, because we're in global coordinates, in case we have transformed that element out of its local coordinate system, we're going to get 2 displacements and 2 forces that spring into being, one in the x direction and one in the y direction. We're going to need that, even though that y direction in local coordinates is going to be 0 for these elements. We're going to need to put it in this format so we can transform that into global coordinates, going back and forth from global to local coordinates. Okay. We then looked and said, okay, we have these transformation matrices, and this is how we transform those local to global elements, and this is how we assemble our global stiffness matrix. Once again, we looked at this for trusses, and the same exact thing applies to springs. All right. Then we saw recalling our truss transformation matrix, how we can transform from local to global coordinates, either our displacements or our forces. We saw how to do that with our stiffness matrices as well. For a one-dimensional truss element, then, we saw this summary kind of slide where we have our local coordinate system, we have our local relations of force to displacement. We can calculate our stresses in one of 2 manners. Remember all that? Okay. Now, this prepared us to go and actually analyze these trusses in 2 dimensions. So while this is a baby step forward, there's a good amount of work to really understand it. So we're going to go ahead and summarize our basic approach then for truss elements, 1D truss elements in 2 dimensions. Okay, that's what we're going to get to here, and then we're going to look at some examples. Here's our basic method for what we're going to call rods in 2 dimensions. Rods is a word used by many finite element codes to indicate an element that has axial stiffness for like a force, axial force only, and a torsional stiffness. Now, in our text where we're doing this by hand, a truss element only has axial stiffness, and we're not going to add that torsional stiffness until later. So these are just axial members, okay? So we're going to start by modeling our system with nodes and elements, which means if we're not given numbering for our nodes, we're going to number them. If we're not given numbers for our elements, we're going to number them. And then we're going to start calculating stiffness matrices and so on. Okay? We then calculate our local stiffness for each element. The easiest way to do this is to focus on the little 2x2 or the most fundamental unit of stiffness matrix for this. We then determine our transformation matrix for each element, our T star. And then we transform that element stiffness matrix into global coordinates, turning that into a 4x4 global matrix. This is probably the easiest way to proceed. Once we have each element in stiffness in global coordinates, we then can assemble our matrix. Now remember this prior step where we're calculating that global stiffness matrix. The easiest way to do this, if you have a calculator that will handle matrices and simultaneous equations, you just have a function where you can put in the angle and it defines your T2 star, and you have a function where you can put in your area and your length, and it will calculate your stiffness matrix, your KEL2. Then you multiply T2 star inverse times KEL2 times T2 star, and that will give you your 4x4 element stiffness matrix. This will prepare the way for later when we have bigger, more complicated matrices. We then number our local stiffness matrices with the node numbers on the rows and the columns, and we number our global stiffness matrix with the nodes on the rows and columns, and then we assemble our global stiffness matrix for our entire structure. We then impose our boundary conditions. If they're homogeneous, we just strike out those rows that are unable to move and columns, and if it's non-homogeneous, we will first impose the homogeneous boundary conditions, and then we will go and decouple our matrix by adjusting however many equations we need to, so that we decouple the matrix that we need from the matrix where we have imposed displacements. Then we end up with a reduced stiffness matrix and a reduced system of equations, which we then can solve for our displacements. Once we do that, we impose our external forces that we know, and we solve the reduced system. We're calling this K sub G subscript R, and with reduced forces, which means the forces corresponding to those displacements, and we calculate the displacements that we don't know. Once we have those, we now have all the displacements, the ones we just learned and the ones that we already knew, and we can use those along with the external forces to calculate what the remainder of the forces are. We then can calculate, we can use the displacements, the global displacements, and the global, to go and calculate what the global element forces are, and then we can transform the global element forces to the local element forces. Once we have the element forces in local coordinates, we then can actually calculate stresses and margins of safety. In this class, I don't believe we're going to be doing much with margins of safety. Mostly getting the stresses will be sufficient for us. Okay? And using either of those two approaches. So that's our basic method for calculating the loads and stresses in two-dimensional trusses and or spring elements. Okay, this is a summary of the final method for rods in 2D. This also includes, this word rods includes trusses and springs. Okay. Now, the book, your text, uses this word bar to refer to truss problems. But generally in finite elements, we reserve that word bar for any member that has transverse stiffness, where it's carrying shear and bending. And we only call members that are axial as trusses or rod kind of elements. So, but you need to be aware of this terminology. Your book talks about this as a bar element. It's really a rod element in terms of finite elements, okay? So a plane truss structure is a structure consisting of axial members, all of which lie in the same plane. We will look at three-dimensional structures pretty soon where they can lie out of the plane, okay? And in this particular case, they're connected by frictionless pins. The reason this is the case is because since these carry no transverse loads, there's no need for moment carrying capability at the nodes. So let's take a look. This would be a typical truss structure. We see we have 3 rods. 3 of them are pinned and 1 is free. We have 1 external load. By inspection, we see we have 3 elements. We have 1 external force. Actually, we have 1 external force shown, but actually that's going to correspond with 2, 4, 6, 7 external forces, because 6 of them are constraint forces, right? We can see we're going to be eliminating 6 degrees of freedom from our model because we've got the U and the V, which are going to get removed at 2, 3, and 4. And only node 1 is going to be free to move in the X and Y direction. Okay? So if we want to look at an example, this is example 3.5 from your text. And this is this little problem right here. We see this is the information. We've got the area of the bar, the rods. We've got the modulus of elasticity of these. And we can see from the picture what the geometry is. Having said that, we're now ready to start moving with our method, which means we're going to start by looking at all the stiffness matrices, right? We want to find our displacements everywhere, which basically is at node 1. So we start by saying, okay, we've got 3 elements and we've got information about each of these elements. Great. We then can calculate the stiffness matrix, AE over L, times our little matrix for each of these when we've transformed this using our transformation. Okay? That's our 3 local stiffness matrices. We then can turn those into global stiffness matrices by applying our transformation equations. Now that we've got these, we can number the location of these and construct our global stiffness matrix. Our global stiffness matrix then will assemble all of those together. We can start by numbering. This is, if we look from left to right, this is U1, V1, U2, V2, U3, V3, U4, V4, and the same numbering going down the first column. And having constructed that, we then can reduce our system by looking and removing all of the constraints. For example, we're going to get rid of rows 3 and 4 because node 2. We can see we've got a constraint at 2. So if this is 1, U1, this is 1, this is 2, this is 3, this is 4. This is UV, 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 UV. This is 1, 2, 3, 4. UV, 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 UV. We can see 4 is constrained, so we're going to get rid of both of these. 3 is constrained. We're going to get rid of both of these. 2 is constrained. We're going to get rid of both of those. And all we're left with is reduced system with the corresponding displacements U and V1 and forces. That gives us our displacements at 1 U and V. Once we have that, we can multiply those displacements times our global stiffness matrix, the entire thing, to get all of our forces. You'll notice the force at node 1 is 0 in the X and minus 10,000 in the Y. That better be true. That just validates that, well, at least we don't have that error. We then see that element 2 has a 0 force in the X direction and a certain force in the Y direction. That's because it has no stiffness in the X direction. That makes sense. At 3 we get 2 forces, one in the X, one in the Y, and at 4 we have only X directional force. Once we have those forces, we then can apply our local stiffness matrices, multiply those by our corresponding global displacements to get the global forces, and then we can transform those into local forces, and then we can multiply by or divide by the area or multiply by that C sub P and get our stresses. Make sense? Once again, your stresses are going to have a sign convention similar to your forces. Don't be fooled. We need to unravel those because those are in the local coordinate system, and you're going to need to look at those and think about them to determine whether they are tension or compression. You can see a tension element will have a positive at node 2 and a negative at node 1. Something that's in compression will be positive at node 1 and negative at node 2. Okay? All right. Here's another example, 3.6. Now this is a little trickier because we have an imposed displacement. This is a non-homogeneous equation. It's a little more challenging. Let's take a look at how this works. So we're going to go through the same process with a little switch up, a little more complicated step in the middle, okay? We're going to start by, here's just an echo of our input properties, and we get our local stiffness. We've got, 2 elements. We've got a local stiffness matrix for each, and then we can transform those into global stiffnesses. Great. Once we've done that, we can construct our global stiffness matrix. Perfect. And then we can go and start eliminating unknowns. We can see at node 2 and node 3, we are not allowed to move. Therefore, we can blow the V and the U direction rows and columns out for both element node 3 and for node 2. That leaves us a 2 by 2. Okay? Now what we want to do is get rid of this, because now you got to watch out this particular problem. You'll notice that the sign convention of this problem is X in the vertical direction from node 1 and Y in the horizontal direction. That's a little tricky, and you got to be careful with that when you report your answers. That will throw you off if you don't notice that. Okay. With that said, what this means is this is free to move in the Y direction, the V direction, but it's given an enforced displacement in the X direction. That means our X displacement is 0.05 meters. Positive 0.05 meters. Oh, it looks like it's coming down, negative 0.05 meters, right? Okay, so we got to be careful here because this is displaced. So what we need to do is we can't just blow that row out. What we've got to do first is decouple it. Now we don't know what the vertical displacement is. The vertical displacement is given by the second row. So we're going to need that equation, but since it has a term in the first spot, we're going to have to decouple it, okay? So we want to remove that row, but in order to do that, we're going to have to do something with this second row, okay? So we're going to go ahead and cover this on the next slide and come back to that, okay? With how we blew that out. We changed this in order to do that, okay? So let's just pretend that we did that step and we can continue. We're going to use this equation because this stiffness term and the displacement is going to be directly calculatable. That's going to allow us to calculate the displacement in the v direction directly. Once we have that, we now have all the displacements. We can use those to calculate all of the external forces. We can use those to go and look at to get our global element forces, which we can turn into local element forces, which we can turn into local element stresses. Okay, that's the entire problem. Now let's go back to that step that we breezed over where we struck out that extra row, and let's look at that on the next slide. Okay, so what we did, we came up with this stiffness matrix, and if we write that out, we see we've got these forces. We've got F1x and we've got F1y. F1y has got the external load P in the positive y. And U1 is 0.05. It looks like it's a positive displacement. And V1 is unknown. So what we need to do is write the equation. We already know we can strike out all these other 4 rows. And this is the coupling that we want to get rid of. We want to get rid of this term U1 in the second row. We're going to do that by writing this second equation. F1y is equal to kg21 times U1, which is 0.05, right? Plus kg22 times V1 plus, and all these other summations are all multiplied by 0, so all the rest of these terms go away. We can now rearrange this and put F1y minus kg221U1 up in our, instead of F1, rewrite that part of the equation. We can solve this, but actually we find it's even simpler for this because this actually is everything we need. We can calculate our displacement directly. If we do that, we find our displacement is this, which can be written this way. Once we have that, we then are back up. We now know all of our displacements. We can get rid of that row, and the prior slide gives us the rest of that problem. Does that make sense? Here's one more example. Here we have a combination of trusses and springs. We have 3 elements then. Element 1 and 2 are both truss elements. Element 3 is a spring. We can see we have 4 nodes, and 3 of them are pinned. Okay, so we're going to first start by getting our local stiffness matrices. There's our and we're going to transform those into global stiffnesses. So we got stiffness matrix for 1 and 2 and 3. 3 is a spring, the other 2 are trusses. We then multiply by the transformation to get the global element stiffness matrix, and then we construct, numbering our nodes. We then calculate our global stiffness matrix. We'll see for element 1, we're going from, for element 1 goes from 1 to 2, right? From 1 to 2. Element 2 goes from 1 to 3. 1 to 3. 1 to 3. Element 3 goes from 4 to 3, right? And so on. From 1 to 4. This is 1 to 4. 1 to 4. And then we can take those and plug those into our global matrix. And once we've done that, we can go and eliminate rows, the rows associated, the X and Y coordinates for 2, 3, and 4. That's going to leave us only 1. Once we have that, we then can calculate solve that reduced system for our unknown displacements, use all the displacements to get all the external forces, use the external forces to get the global forces in the elements, turn those into local force in the elements, turn those into stresses. That is how we analyze trusses in 2 dimensions. We now can calculate 2-dimensional trusses, whether they are truss elements or spring elements. Okay, this is a critical skill, and we're going to build on that, going to more complicated elements moving forward. Enjoy.